words in the corpus, and our standard notation is we have big N, uppercase N tokens. We have V types, V for vocabulary size, and we count each type how many times it occurred, and we expect to get a zip-like distribution, which is a long-tail distribution. A few things occurred many times. The word there occurred a gazillion times. The word off occurred half a gazillion times. And then other words occurred fewer and fewer, and then you expect many, many words that occurred only a handful of times, and specifically a very large number of words that occurred only once. Just to give you a rough idea, something like the Brown corpus, which was considered at the time a balanced corpus of English, in that it was a combination of multiple genres, some fiction, some newspaper, some legal proceedings. Number of tokens was a million word tokens. Number of types was, I think, about 50,000. And the number of those 50,000, those that occurred only once, were a significant fraction. I don't remember, it was 20 or 30, maybe 30,000, 35,000. A large fraction of word types occur only once. And of the remaining, a large fraction occur only twice. And of the remaining, a large fraction occur only 3 times. So it's a very, very heavy tail distribution. And we can draw it like this here. Occurred once. So this would be number of types. And here would be what we called n sub 1. So these are the words that occurred once. And here would be n sub 2. And here would be n sub 3. N sub 4, so forth. This is count is 1, here the count is 2, here the count is 3, this count is 4. 2 equalities that hold kind of trivially. If you sum n sub r, for r goes from 0 to infinity, what do you get? Which is? V. This is the number of types. Every type falls into one of these categories. It occurred only either once or twice or 3 times or 0 times. Well, if the vocabulary is defined only as words that occurred 1 or more times, then it would be 1 here. What do you get if you do this? N sub r times r. R goes from 0 to infinity. Now you get n. Now we're counting tokens. N sub r words occurred r times. So this times this is the total occurrences of the words that occurred r times. Right? Now I can start with from 0 regardless, because r equals 0 will be 0 here, so it doesn't matter if I start from 0 or from 1. There is also a visual, a geometric interpretation of that. Think of the y-axis as types. What will the token space be? Area. So if this is 1 wide, but this is 2 wide, and this is 3 wide, and this is 4 wide, and so forth, every square is a token. Right? So if you want to count tokens, calculate the area. The area is 1 times n1 plus 2 times n2, n sub 2, plus 3 times n sub 3, and so forth. So let's say the word beer occurred twice. Beer and beer. These are its 2 occurrences in 2 different places in the corpus. Some other word occurred 3 times, and so forth. So think of height as number of types, and area, or number of squares, number of cells, as number of tokens. So the overall area occupied by this kind of chart is proportional to the size of the corpus, the number of tokens, and the height of the different categories is the number of types. And if you put all the categories on top of each other, you'll get the total number of types. Okay? This is called the frequency of frequency chart. Frequency of frequencies. It might go by other names too. Count of counts, I think. Now the question I asked you, the experiment I asked you to do, and in fact I'm asking you to do it in your homework, is to take a fixed unigram distribution. So assume that the distribution of the words is fixed and known. Well, let's say it's not known to you, but it's fixed. And you can sample from it. To be consistent, I should put a big W here. Remember that the big letters are the random variables, and small letters are occurrences. So if I do, I'll add it here to the notation. Wj means the random variable that takes on 1 if the word is, well, I'm sorry, W in general is a random variable, and the values it takes are from W1 through WV. So the value it takes is which of the words in the vocabulary it is. And I'll use small w for running index. So Wi is word number I, in token number I in a sentence. So now I ask you to pay special attention to this category. Call it the singletons. These are the words that occurred exactly once. And I'm sure you would agree with me that different corpora will define different singleton groups. So it's not like a property of the language. It's a property somewhat of the distribution, the fixed distribution, but it's also a property of a particular corpus. So let's call it my singletons, to kind of remind us that this is what I got in my current experiment. And now I'm asking you to go back to, so the story that happened was that you drew some random sample from this distribution. You collected that corpus. You calculated the frequency of frequencies. You identified your singletons. And then you're about to draw another word. And I want you to tell me what is the probability that the next word that you draw will be from your singletons. Next word will be from this list of words. And the maximum likelihood estimate of that, P word is my singleton, or your singleton, whatever. Do you remember what the maximum likelihood estimate was? It's the relative frequency. What's the relative frequency estimate? It's n sub 1 over big N. Right? N sub 1 here is used as the number of times these words occurred so far. It's n sub 1 times 1, actually. But times 1 is... It's the area here divided by the overall area. But we concluded that this estimate is biased high. And we're a little confused because maximum likelihood estimates, relative frequency estimates, are not supposed to be biased. And generally they're not biased, but if you chose the category after you saw the data, they could be biased. And here they are biased. And we're not talking about a small theoretical bias. We're talking about a factor of 3 off, or factor of 4, or factor of 5 off, depending on the size of your corpus. So let's rehash this notion and take it to an extreme. What is the probability of any person in the country to win the lottery? The answer is very small, 1 in several million. What is the probability of the person that we know won the lottery? Oh, the lottery, yeah, it's 1. Right? I mean, if you already know something about them, then the old rules don't apply. And here we know something about them. But what do we know about them? We know that they are rare. We know that they occur rarely. So you would think that the bias should be in the opposite direction, that we should, that we're going to be biased low. But no, we're biased high. And the sort of not quite proof, but argument that was made here was that words that did not occur at all are definitely biased low. And somebody has to pay for that. If somebody is biased low, somebody else has to be biased high. But why are they biased high? Why are words that occurred once biased high? Why are words that occurred twice biased high? So now let me talk to you about the paradox of the regression to the mean. How many of you know what a regression to the mean is? Very few. Okay, I don't know if it's good or bad. I guess it's good. You would enjoy this, or you will learn something from it. But it's bad because you should all know what it is, because it's a very important phenomenon. So you go to a high school, and you're trying to identify the smartest kids. So you give everybody an IQ test on a particular Sunday morning in February. Sunday, no. Monday, February. You give them an IQ test, and not surprisingly, the results come back, and they are Gaussian distributed, more or less. It looks like a normal distribution. So here's the IQ test. This is 100. And results look like this. This is as close to a Gaussian as I'll ever be able to draw. Now, of course, it's not like this. It's a finite population, but it fits this more or less, you know, with some wiggle here. And you're interested in the smartest kids. So you go to this range and you take the 5% of the overall kids that are the smartest, that scored the highest. And you take their average IQ, and the average would not be exactly in the middle of this because there are more kids here than here, but the average would be, I don't know, 130. It depends on which IQ test you use, by the way. All IQ tests are sort of calibrated to have a mean of 100, but they have different standard deviations. So the meaning actually depends on the test. Let's say it's 130. And just to be sure, since there are fluctuations and stuff, you come back a month later and give them a different IQ test. Very similar idea, measures same skills. This is a very large school. It has 1,000 students. So the 5% is 50 students. So we're talking about a large sample. You give these 50 students another IQ test. And you look at the average again. What do you think happens to the average? Will it be roughly, it won't be exactly 130, right? Would it be more? Would it be less?
I think it'd be less.
Less. Why?
Well, because some of them may have gotten lucky the first time, and then the second time, it's more like reality hits, but you're still looking at the same type of people.
Okay, but some of them may have gotten unlucky too.
That's true.
But the unlucky ones didn't get to take the second test.
Ah, so you've got something there. So the answer is that this is true. The second test, the result is going to shift back towards the mean. It's called the regression towards the mean. The second time you give them the test, they're going to be dumber. Okay, and of course they're not dumber, but it's almost guaranteed when the set is large enough, the average would be less than it was before. What happened was that in any one test of one student, there are two components, that their innate skill, and then there's what we call luck. Whether they had breakfast that day, whether they slept enough, whether they happened to know that particular question, all these things that change from test to test. A more accurate way of representing it is the things that don't change from test to test, and the things that do change from test to test. And we're going to assume that things that change kind of randomly, maybe even with the Gaussian distribution. Not necessarily, but it could be. So a particular student has a true IQ of, say, 125, and the test IQ would be the true IQ plus or minus some randomly distributed value that has to do with how much sleep they got and other random factors. Some, zero mean and some standard deviation. So if you look at the true, let's use some color here. These colors are not going to be related to the colors of random variables. I'm going to deliberately use colors that we don't use there, so let's use purple. If you look at the true distribution of IQ in the classroom, I'm not even talking about the population, the true distribution in the classroom, let's say it's the purple one, and then on any particular test day, every student, let's say this is their true IQ, they build a little Gaussian bubble around it. And the result they give you is somewhere in this bubble. Right? They draw from a Gaussian distribution, and they end up either here or here. So they could be a little more lucky, a little less lucky. They could score a little better than the true value, a little less than the true value. Okay? And this bubble could be pretty large for all we know. And we can measure that, right? We can take a student and give them exam after exam after exam, and now we're going to complicate the fact that they're going to learn how to take this exam, but we can do it with a large number of students and just test them 3 times, and we can estimate the standard deviation of that bubble. And every student has their own bubble. And when they all draw from their bubbles, the result would be very similar to the original purple. But it has the following property, that conditioned on the fact that you ended up getting a high score, let's say, okay, let's put it this way. Let's say that every student either got a little lucky or a little unlucky every day. Okay? Could have been either more lucky or less lucky. On average, you're as likely to get more lucky than less lucky. I'm going to ignore the fact that how much you're going to get lucky or unlucky. It's also going to be symmetric. It's a Gaussian distribution in both directions. But let's just simplify and say that every student either takes a step to the left on the scale or takes a step to the right on the scale, 50-50. Okay? It's still going to be the case that if I look at people in the extreme right tail of the scale, I'm going to find more people here who got lucky than people who got unlucky. Why? Let's take any one of these people. The person here, right here. He could have come from the left, he could have come from the right. But there are more people on the left in the true distribution than there are on the right. So chances are the person here is more likely that it came from the left than it came from the right. So the true average of the average of the true IQ of people who scored well is actually lower than what they scored at any one time. Of course, the same thing is true on the other tail. People that you will label as dumb, you will find that they have improved, quote unquote, on the second test. Because you define them as dumb relative to the first test. You could reverse the order of the first and second test. It doesn't matter in what order you apply them. If you define kids as geniuses and dumb based on the second test, you will find that their score, their average score on the first test, moved more towards the mean, towards the center. The amount of movement depends on how far into the extreme you went. But it's non-zero at any level. Even if you took everybody from 100 and up, and you average that, you'll get something around here. Now you keep your eyes on these people only, and you give them another test, and chances are the average will move to here. You can take it to an extreme. Suppose everybody really has the same IQ. Everybody is exactly 100. And those bubbles are big because it's influenced by random luck, sleep, food, mood fluctuations. Then you will get a Gaussian distribution for every test that you do. And you will identify the super smart and the super dumb, right? But you and I know that this is completely random because everybody has exactly the same capability, and therefore any group that you identify, you test them again, they're going to tend towards being distributed again in the middle. So how strong this phenomena is depends on the relationship between the distribution of the true IQ, the true latent variable that you're trying to measure, and the distribution of the noise that's added to the measurement. Any questions about this?
I think that the extreme case when we all have the same IQ will look very suspicious because the true variance will be very low. It would be like a peak. So it will not, like, so people will, it will not look like a true value. It will be more like a peak, a very narrow peak. And the more
The true value, I assume that everybody has 100 IQ, so the true variance is 0, right? I assume the extreme case where the true distribution of IQ is delta function around 100, 0 variance. And now I give the exam, I get a Gaussian distribution of scores, I take the kids that are the extreme good side, and I give them another similar exam. And their average is going to be around 100.
yeah, that's right. But like looking at the scores, everybody will look approximately the same. It will be very narrow peak.
Well, you're assuming that the noise in the measurement is small. What if the noise is large?
Well, yeah, that's actually maybe personal variance will be large.
Well, suppose I give them an exam consisting of just 2 questions. You know, I can deliberately make it large. Okay, so now let's apply this idea to what happens here. A word, let's say the corpus was 100 words, I'm sorry, 1,000,000 words. So n was 10 to the 6. Let's think about words whose true probability in the language is 1 in a million. If the true probability in the language is 1 in a million, and you collected a corpus of 1,000,000 words, on average you expect to see them once. In practice, you will see them either 0 times, or 1 times, or 2 times, or 3 times. There will be some kind of a distribution. If you saw them 0 times, you could say that they got unlucky. If you saw them 2 times, you could say that they got lucky, because you saw them more often than is expected by chance. If you saw them 3 times, you say they got very lucky. Now you see a word once. What are the chances that it got lucky versus what are the chances that it got unlucky? Let's assume that words, for simplicity, fit into categories. Either they tend to occur 1 in a million, 2 in a million, 3 in a million, 4 in a million, or 1 in 100 million, you know, extremely rare. Or let's say just 1 in 10 million. If you saw it once, it could have come from those words that occurred 1 in 10 million and gotten lucky, or it couldn't come from those that were 1 in 2 million and gotten unlucky. Which one you're more likely to see depends on how many there are of each type, right? Here is a concrete example. Suppose there are only words, there are words that occur half of 10 to the 6, 1 times 10 to the 6, and 2 times 10 to the 6. You saw a word once, and you wonder which of these categories it came from. To calculate the posterior, given that you saw it once, which category it came from, you need to know the priors on the categories. Under conditions where there are many more of these than of these, and many more of these than of these, when you see a word once, it's more likely that you got lucky than it got unlucky. And that's the conditions we have in natural language. Because of the long tail, events that occurred very few times, chances are they got more lucky than they got unlucky. They were biased high. How much? Well, that depends on the prior. So it depends on the form of this distribution. You know, how are there many more words with this probability than words with this probability, and many more with this probability than with that probability? That depends on the language. It depends on the genre. But in natural language, it's almost always the case that the tail is so long that any event that occurred once or 2 times or 3 times consists of lucky, is biased to be lucky rather than unlucky. And therefore, an unbiased estimate of it would be shifted down. By how much? Well, actually, there are ways of correcting. There are formulas for doing that are pretty good, so I'm going to teach you one of them. This formula is actually due to Turing, the famous Alan Turing, the sort of father of computer science and AI. It was published by I.J. Good, who's a British statistician and was a friend of Turing and a colleague. And I.J. Good published the formula and described it, but he attributed the idea originally to Turing. So it became known as the Good-Turing formula. And here's the logic of it. We want to know, we want to estimate the probability that the next word will be singleton. Be a singleton. So we imagine that the corpus was collected one word at a time, all coming from the same original distribution that's fixed, unknown to us, but the corpus, the individual words were collected independently of each other. So each one has the same probability. And we say, what is the probability that the millionth and one word, we collected million already, what's the probability the next one will be one that was until now seen exactly once? And the answer is, it's probably very, very similar to the probability that the last word we collected, the millionth one, was also seen only once. Because that event, finding a word that occurred only once until now, is an event that does not depend as much on whether you have 1,000,000 or 1,000,001 words, right? Or 999,999. So I'm going to make this very tiny approximation. And I'm going to say that this is almost exactly the probability that the last word encountered. This is the next word encountered. This is the last word encountered. Was a singleton. If somebody told you that the last word encountered, the last one of the corpus, was a singleton when it was encountered, where will you look for it in this chart? First column? The last word encountered was a singleton means that when you encounter the last word, you've already seen it once before. Exactly once before. Second, right? Because you encountered it, it became the second word. So if the last word encountered was a singleton, that means it is now hiding here somewhere. Now, since the probabilities are independent, the order of the sampling is independent, so any order of the words is the same as any other order of the words, then the probability that the last word you saw is one of these is simply the number of squares you have here divided by n. So that would be n sub 2 times 2 divided by n. Somehow we shifted from talking about singletons to talking about doubletons. It was very clever. You can use the same idea to answer the question, what is the probability that the next word will be a doubleton? By will be a doubleton, I mean will be a word that is currently classified as a doubleton. Of course, once we encounter it, it will become a tripleton. And I'm going to approximate this similarly. It's about the same as the probability that the last word encountered was a singleton, a doubleton. And the probability of that is n sub 3 times 3 divided by n. And I can keep going, right? But I can also go in the opposite direction. I can also ask the question, what is the probability of the next word being a zero tone? Next word will be a zero tone. And another word for a zero tone is a new word, a word I have not seen before. New. The probability that the next word will be new, namely will come from this column whose height I may not even know, is about the same as the probability that the last word was new. What is the probability that the last word was new? Well, if it was new, it is now a singleton. So it's the area of this tall column, which is n sub 1 over big N. So this gave us a very nice estimate of the probability of novelty, the probability of encountering something that we have never encountered before, even in situations when we don't know how big the vocabulary is. We do not need to know what the vocabulary size is. This is actually, I think, quite remarkable. Even more than what it does for us here, it's what it does for us here. Because the maximum likelihood estimate of a new word is what? Zero. If you relied on relative frequency, or maximum likelihood, for estimating the probability of novelty, you will always be told that what never happened is never going to happen. Right? But we know that's not true, and this gives us a very nice estimate of the probability of something that has never happened will happen, under the conditions of these long-tail distributions, which are very prevalent in language, and in many other areas, by the way.
So does that take some of the probability mass out of the rest of it?
Yes, it does. Yes, it does. We're going to see it in a minute. But absolutely, it does. And they all have to sum to 1, right? Because the estimate has to be consistent with itself.
I understand that the last word was new as the last word was a singleton.
Well, new means zero tone, right?
Yeah, I mean the last word was new.
Why? How do I get to here?
Yeah.
Because if the last word I added to my corpus was a new word, a word that never was seen before, after I added it to the corpus, how many times was it seen?
One.
Once.
Yeah.
And therefore, it got into here.
Yeah. I mean, so this last word was new was before you added,
Yes.
and the one last word was doubleton is also before you added.
Yes. Yes. I'm sorry, I should have made that clear. When I say the probability that the last word was a doubleton, I mean was a doubleton relative to the frequency table as it existed before I added that word. Yes.
But before you find this probability, you have already got this that chart, or you are counting while you draw this chart while counting. I mean, as you.
Yes. Yes. I do keep track of this chart as I'm adding words, and I modify and I move things. So the first time I see a word, it gets added to here. The second time I see the same word, I take it out of here and put it here, and then I take it out of here and put it there. Yeah.
So as you count, as you encounter new words, that big N and the N sub 1, N sub 2
Change all the time.
Okay.
Absolutely. You could, by the way, you could use this estimate to draw a curve of the probability of all these events as a function of n. It might not make sense to talk about it in the first, 1,000 words, because the smoothness criteria that are needed for good tuning to work may not be satisfied there. But after you collected a relatively small number of words, you can start tracking, first of all, the probability of novelty. Namely, the probability the next word you see would be a zero tone relative to what you've seen so far. And that probability starts fairly high and will go down with time. This is the probability of novelty, also known as probability of out of vocabulary word, if your vocabulary is defined by the words you saw so far, right? If your vocabulary is defined externally by somebody else, then you need to reconsider. But very often we define our vocabulary by the words we've seen so far, and we're concerned about what are the chances that we're going to see a word that's outside our vocabulary. Well, we have that estimate. It's n1 over n, where remember that n1 over n, both the n1 and the n change as n grows. So they're a function of the accumulating corpus. But at any point in the accumulation of the corpus, you can stop, calculate n1 over n, and gives you an estimate of the probability of novelty. You can also draw in the same chart the probability of one step above novelty, namely the probability the next word you see will be one that was only seen once until now. And that might be, I assume, higher, and also goes down. So this would be P of singleton. And again, what I mean by P of singleton, or what I mean by the event singleton, means you encounter a word that until now you've seen only once. Once you saw it, now you see it twice. So it moves to the doubleton column.
According to this formula, what happens to the word which is seen most often?
The word that's seen most often is not here, but it's like way there in Erie, PA, right? So it doesn't need to be adjusted. Using relative frequency will be perfectly fine, because theoretically it needs to be adjusted, yes, but the amount of adjustment would be minute.
In practice, you only do this for the first 3 or 4?
5, 6, I like to do 7, but the biggest impact is on the first. The infinite impact is on the 0 case, right? Because you move from 0 to some positive estimate. But the singleton case is also a very significant impact. I mentioned it could be a factor of 3 or 4 or 5. So in a typical corpus, if you assign words that occurred once a probability of 1 over the size of the corpus, you will be overestimating them often by a factor of, say, 5. And a better estimate would be as if they occurred 0.2 times out of the size of the corpus. Okay? It's a big factor. When you look at things that occur twice, it won't be a factor of 80% discounting, 80% reduction, but maybe 30% or 40%. If you look at things that occur 3 times, it'll be maybe 10 or 15%. By the time you get to 5 or 6, it'll be a tiny percent. But for things that occurred very few times, it's a big difference.
If you put this on a log scale,
Mm-hmm.
could you sort of predict how big the vocabulary is where it crosses 0?
That's a good question. I don't think you can do it from this, although Good published also a paper about estimating the size of the vocabulary from this, but I don't think that's the technique he used. What you can do is estimate perhaps how big a corpus you need to have in order to drop the novelty rate below a certain threshold. You want new words to come up at no more than once in a million, okay? So, okay, I need to grow this much. Maybe. If this is a straight line, I don't know what it is in log scale. It's a fair point. So now is the time to tell you an interesting historical curiosity. Good published this paper not in the domain of language, but in the domain of biology. The name of the paper is something about estimating the frequency of species. So the model is a biologist of the old type, not the molecular biologist, but the guy who chases butterflies with a net. Goes into a forest and chases butterflies with the net and collects beetles and bugs and all kinds of stuff. And they want to map the species of the forest and their frequencies, just like the species of words and their frequencies. So they collect a lot of bugs, and they spend years in the forest, but at some point they get tired and lonely and want to go home. And the question is, when is it good enough? When can they go home? So they say that, okay, when I get to a point where I find a new species only every month, then it's not worth my time and I'll go home. So they need to estimate the probability that, you know, in the next month worth of bugs that they catch, of tokens, there will be a new type. Okay? Or they want to estimate the true prevalence of a particular bug, given that they only caught one in a sample of 500 bugs. Okay? So it's very similar. So he published it as in a Journal of Theoretical Biology, and that was in the 50s, I think. And people working on speech recognition and on language modeling discovered this paper and said, hey, that's applicable not just to bugs, it's applicable to language too, and we can use it to do mathematics with language. Little did they know that actually Turing did not work on this problem for bugs, he worked on this problem for words. Because Turing, during World War II, worked on breaking the enigma, breaking the German code and the Japanese code. So he built a whole theory of language modeling, and part of it was estimating rare events. But he couldn't publish it because it was confidential. So he told his friend Good, who was not part of that effort, and I don't know who decided to switch to biology, and they just planted the problem in biology and published it. And other people discovered it and moved it back. So that's the story. Okay, so this is called the Turing formula. It's a remarkably simple and remarkably accurate formula in the sense that there's been a lot of work on deriving it in many different ways. There's one famous paper on 3 ways of deriving good Turing formula. I think it's unbiased, in some sense of unbiased. I don't know exactly. I don't know the theoretical properties, but I know that in practice it works exceedingly well, and your assignment will prove it to you. You will actually do it, exactly the experiment that I described here, and you'll compare your good Turing estimate with your maximum likelihood estimate. One thing I need to mention is that so far I did not try to estimate the probability of any individual word. I tried to estimate the probability of a classes of words, like the probability the next word will be a doubleton. That means that the next word will be one of the words from this set, right? If I want to estimate the probability the next word would be a particular word, let's say the probability that the next word is the word beer, conditioned on the fact that beer so far occurred 2 times. I already said that the probability the next word would be one of these words is n choose 2. Sorry, doubleton would be, comes from the tripleton, so it's n choose 3 times 3 divided by n. That was the probability that the next word would be any word that was seen twice. But now I want it to be one particular word that was seen twice, and I have no other way of distinguishing between all the words that occurred twice. All the words that occurred twice are equally likely. So any one of them, I would divide here by n choose 2, n sub 2. Similarly, for words that occurred once, what word did they say occurred once? Aardvark. Probability the next word would be aardvark, given that aardvark occurred once. So we first use Turing formula to say that it's n choose 2, n sub 2 times 2 divided by n. And then we have to divide by the number of words that occurred once, which is n sub 1, to get the probability of that particular word. So that I would call the good Turing estimate, GT. Right. So for the words that haven't occurred at all, we just want it to be novel. Novel is n sub 1 over n. Now, if you happen to know the vocabulary, then you could divide it here by n sub 0. And know the probability of each one. Well, I say no, estimate the probability of each particular one of these words. If you don't know the vocabulary, then you don't know n sub 0. And then you can't derive the probability of any particular word. In fact, n sub 0 could be infinite, right? When I say derive the probability, it could very well be that the probability of beer is actually much higher or much lower than what we did here. This is just our estimate. And since we have no way of distinguishing beer from any other words that occurred once or that occurred twice, we're going to make the uniform assumption in that set. Yes?
So you mentioned that we're updating the chart as we process our corpora, but we're going to calculate the probabilities after we've seen everything, and we're going to use the final chart, right?
Right. Right. In practice, you do not need to calculate it along the way. You just have the corpus, you calculate it at the end. I'm just saying that as a thought experiment, you can do it along the way. And it's a way of deriving good Turing formula, is doing it before you add the last word and after you add the last word. But the end result is take your whole corpus, sort it, count the occurrences of each word, calculate n sub 1, n sub 2, n sub 3, n sub 4, up to n sub 6 or 7, and that's all you need.
But according to this smoothing technique, and most often you want to smooth for particular words which have never been seen before, you want to assign a probability, say in a language model, to a word you have never seen before, whether as a unigram or a bigram or whatever. If you don't know n0, then basically you're screwed, right?
Well, yeah, but I would ask you, why would you want to assign the probability to events that you don't know how many there are? I mean, I think it's very powerful that you know that all of them together should be this much, right? That's usually all you need to know. Maybe not. I mean, it would be nice if you knew the size of your vocabulary, but, and even if you know the size of your vocabulary, it's not that all the words you have not seen are equally likely. They're probably not. But you're right, you're screwed in the sense that I cannot say anything anymore beyond what I said here. Now, a few caveats. The good Turing effect, or the good Turing formula, which is a correction to this effect, has nothing to do with the fact that the vocabulary is not always known. It is not a function of the fact that the vocabulary is open. Yes, in language the vocabulary is open and is often unknown. But even in situations when the vocabulary is fully known, this effect is still there and very strong. So it applies not only to individual words, but for example to word pairs, contiguous word pairs, bigrams or trigrams. So let's say you have a fixed vocabulary, 200,000 words. It encompasses most of English, and anything that's outside that will throw away or will convert into a single symbol. Fixed vocabulary, okay, no open vocabulary. If you count the number of bigrams, so you can talk about bigrams tokens and bigrams types, right? The words of the, or Buenos Aires, or New York, or ping pong, or any combination of words occurred a number of times in a corpus. So that these are token occurrences. And you can list all the types. If your vocabulary is fixed and known, it's 200,000 words, the number of bigram types is 200,000 squared, right? Every word can be followed by every other word in principle. 200,000 squared is a very large number, right? It's 4 times 10 to the 10, okay? Of course, in any corpus, the majority of them will not occur. So you have a huge n sub 0. And of those that do occur, the majority of the bigram types will occur exactly once. Huge n sub 1. And of the remaining, the majority will have occurred twice. And of the remaining, the majority will occur 3 times. And if you want to estimate the probability of a particular bigram that occurred once, the good Turing formula of n1 over big N will give you a far better estimate than the relative frequency formula of 1 over n. Nothing to do with open vocabulary. The vocabulary is closed. It has to do with the fact that the vocabulary is very large, and there are many words that occurred very few times. So we're not only talking about vocabularies, we're not only talking about individual words. In any phenomenon in language where there's lots and lots of categories, such that there are many categories that are seen only once, and there are many categories that are seen only twice, and that as you see more and more data, you encounter new categories. Whenever you're in that situation, this phenomena is very strong, and you should use good Turing discounting. You should use the good Turing formula rather than the maximum likelihood formula. When should you not use it? When the size of your sample is large enough relative to the number of categories that you don't have this long tail anymore. Let's say your language has only 1,000 words, and you saw 1,000 word types, and you saw 1,000,000 tokens. Unless the distribution is super skewed, even if it is slightly skewed, chances are you saw many examples of every category, of every word. So if you look at, in these situations, the counts here are all going to be 0. You saw nothing exactly once, and nothing exactly twice, and nothing exactly 3 times. The smallest number of times you saw something was 50 or 100. When that's the case, good Turing has nothing to tell you, and relative frequency is perfectly fine. But when you have this kind of distribution, you should use good Turing. And in language, we almost always have this kind of distribution. If you think about distribution of sentences, fragments, even individual words, but everything that consists of combinations of words, parse trees. Okay, we talked about the fact that words that events that occurred very few times will be corrected to a probability, we're going to be down corrected. And events that occurred 0 times will be up corrected. And of course, to give a consistent estimate, you will need to make sure that everything sums to 1. So it will not happen automatically. You will need to sort of normalize the distribution somehow. And the original paper also does not rely on these counts because they can fluctuate somewhat. If you have a very large corpus, then you can rely on them. If the corpus is a little smallish, you may want to smooth it. And what Good does in this paper is he marks these points, and believe it or not, this is a paper from the 50s, he kind of passes a smooth line through it to smooth it. And the reason is, if you go further out, you would start having like holes here. Like this, nothing occurred. This is 4, this is 5, this is 6. Nothing occurred 7 times, and then something occurred 8 times. So if you want to keep going a little further, he smoothed it with a smooth curve. I don't think he even used a parametric curve. Remember, he didn't use computers. He kind of did it by hand. But he basically smoothed it and used the smooth value, and that's a reasonable thing to do. In our case, with the size corpora we have today, you don't need to worry about it because it's going to be smooth to quite a long far away, depending on how big your corpus is. But even a small corpus of 1 million words, it's going to be smooth up to here easily. There's something that tells me, for some reason I'm thinking that I'm forgetting something here. Is this the right formula, Yun?
Yeah.
Yeah? I'm not forgetting anything here? Okay, I don't know why I'm... Okay, so this is one form of smoothing. I'd like to talk to you about other forms of smoothing of maximum likelihood estimates. Until now, we talked about probabilities of individual events, but I'd like to change it to generally discussing estimating a multinomial. Question, comment?
Yes, so as far as I understand, I can estimate for the number of occurrences or double right? And 2 times divided by
You correct the maximum likelihood estimate by using this formula, yes?
So this should be downward correction, right?
Yes.
So which means that these numbers and I by I is actually a decreasing function of I, at least for some relevant values.
Right, so n2 is less than half n1. Right? So that's a good thing that you brought up. Compare this n2 to the maximum likelihood estimate. The maximum likelihood estimate would be 1 over n. Right? This is the probability of the next word was seen once before. A particular word that was seen once before was 1 over n. So yeah, now you compare these two, and it's 1 here, and it's 2n sub 2 over n sub 1 here. And I told you that this is smaller than this, almost for sure. So that means that n2 is less than half of n1. And that is true. But it's not true here that n3 is less than a third n2. I think that I'm missing a factor of 2 here, and I'm trying to understand why. I think I'm wrong here.
According to the Zipf's rule,
Uh-huh.
n3 times 3 should be somehow equal
Uh-huh.
or proportional to n2 times 2.
To n2 times 2, right.
Then
Right. I've only taught this 12 times before. And
somehow such a distribution of
all right. The probability of the next word would be a doubleton. It's probably the last word about a doubleton. The last word is a doubleton if it's now a tripleton. And if it's now tripleton, the chances it was the last word was this times this divided by this. This one is true.
Actually,
And now?
I think that the Z-floor is about distributions. It's not only about the rank. It actually tells you how the probability depends on the rank. But the problem is that actually the Z distribution cannot be sustained like in the long run. And in the long run, you need something like a Mandelbrot distribution with coefficients power coefficient larger than 1, because otherwise it doesn't converge. If you have an infinite number of words, you cannot model it with the Z distribution.
Yeah, but the problem there is actually that the number of occurrences gets discretized. So it cannot be 1 over rank, which is continuous. It has to be 2, 1, 0.
Right, ZIF this deals with the rank, not with how many times it occurs. So that's a little different, because the rank is cumulative occurrence, right? So it's a little different. Let me leave you with a little doubt here, and if it turns out I was wrong, I will send a correction this afternoon. Okay? Let me move on to other forms of smoothing. So a multinomial, x is distributed as a multinomial with probabilities P1, P2, Pk. That's basically a unigram, right? It's a distribution over individual categories such that the PIs sum to 1. Until now, we thought about it in terms of pick a particular word and estimate P of that word. So these are the words in the vocabulary, say. Word 1 through word V. But I'd like to think about it more generally as picking a point in an n-dimensional space that represents all of these probabilities. So we can think of any particular multinomial, any particular array of probabilities as being represented by a point in k-dimensional space. The ith dimension is where Pi is. Okay, so every point in the k-dimensional space represents the entire multinomial distribution. Not every point in the k-dimensional Cartesian space corresponds to a bona fide distribution, right? First of all the coordinates have to be positive. Second, they have to be less than 1, right? All the PIs must be between 0 and 1. So this restricts us to the positive quadrant of that space where everything is positive. And further, it restricts us to the positive cube quadrant of that space. No value is more than 1. But even that is not enough, because if you take a point that you generate randomly where all the PIs are between 0 and 1, there's no guarantee the PIs together will sum to 1. So you want them to somehow sum to 1. And it's a very small subspace of the full Cartesian space. We don't even know how to visualize it, but we have a name for it. It's called the probability simplex. The probability simplex in k dimensions is the set of all points in k-dimensional Cartesian space that correspond to a bona fide probability distribution. Namely, that all of their coordinates are between 0 and 1, and the sum of their coordinates is 1. Now, the probability simplex is an example from geometry of something that's called the manifold. A manifold is a subset of the n-dimensional space. The subset itself may be of lower dimensionality. But it's not necessarily a neat subspace. Like if this room is a 3-dimensional space, the floor is a very neat subspace of dimensionality 2. It has only area, it doesn't have volume, right? But if I put like a wavy surface through the room, it also has 2 dimensions. It has 0 thickness. It's just a space, but it doesn't fit neatly into the floor or into the ceiling or into the sides. But it is manifold. So manifold is a more general subset of the space that has lower dimensionality. The probability simplex is a manifold of what dimensionality? k minus 1. You can see that because it has k minus 1 degrees of freedom. You can choose k minus 1 probabilities not in an unlimited, unrestricted way because you cannot exceed 1 in the sum, but you have infinitely many choices for each one of them. And the last one is fully determined. So the probability simplex in k dimensions is a k minus 1 dimensional manifold in the k-dimensional embedded in the k-dimensional Cartesian space, which the k-dimensional Cartesian space can be written as r to the power of k. And it's actually only the positive quadrant of it, so it's r plus to the power of k. Or you can say it's inside the 0 to 1 to the k, right? So it's in the space that's represented by the intervals from 0 to 1 along each one of the dimensions. So it's like a unit cube that's one corner is at 0, 0, 0, 0, 0, and the opposite diagonal corner is at 1, 1, 1, 1, 1, 1. But even that is not enough because we're only we're a lower dimensional manifold, which means has the property that if you choose uniformly a point in this space, the probability that the point you chose is a bona fide probability distribution is 0. Right? Because if I pass a manifold of second dimension through this room, if I choose a point at random in this room, the chances that it's exactly on the manifold is 0 because the manifold has 0 width. I cannot visualize for you more this probability simplex in k dimensions, but we can visualize it in very low dimensions, and it's worth doing. So let's start from the lowest possible dimension we can. 2 dimensions. K equals 2. 2 dimensions means a multinomial that has only 2 outcomes. What do we call a multinomial that has only 2 outcomes? A binomial. So we're back to the coin, head and tail. There's P1 and P2, but we don't have to call P2 P2. We can call it 1 minus P1. So this demonstrates to us that there's only one degree of freedom. We can just choose P1, any number between 0 and 1, and the other value is automatically determined. Suppose this is P1. Let's make it smaller. This is P1, and this is P2. Because P2 has to be 1 minus P1, here's 1, here's 1. The points that satisfy that lie along this diagonal line. The full 2-dimensional Cartesian space, or in fact the positive quadrant on this area, the 0 to 1 to the power of 2, is this entire block. This block is the r, or actually the 0 to 1 to the power of 2. This line is the manifold of dimensionality 1. It's a line, therefore it has the dimensionality of 1. It's a manifold of dimensionality 1 that is embedded in this 2-dimensional space. Every point on this line corresponds to a particular binomial distribution, and every binomial distribution in the world corresponds to a point on this line. Okay? So the entire probability simplex in 2 dimensions is this line. Well, this was easy. Let's try to move to 3 dimensions. My limitations will become evident in a minute. I don't know how to draw in 3 dimensions. Maybe like this. So this will be P1. This, say, will be P2. And this will be P3. The maximum value you can get on P1 is here, 1. The maximum value you can get on P2 is 1. Maximum you get on P3 is 1. And now I'm going to connect them with something like a triangle. And I'd like you to try to see this as a corner of a room, where this corner is the furthest away from you. And this triangle sits diagonally on that corner. So it would be, you won't see the corner if this is the probability simplex. It is a triangle. It lives in 2 dimensions. It's a 2-dimensional creature. And it's embedded in this 3-dimensional room. If I were to do it in this room, I would take something 2-dimensional, but preferably a triangle, and I will go to the corner. You can see that corner better. What I drew but there on the board was supposed to be that corner, and this is going to sit diagonally here and touch. Is it better now?
Yeah, I get a cable.
Is this new cable already or no?
No,
Okay.
I gotta get one.
Okay, can you hear me now?
Yeah.
Okay. Yeah, when I become athletic, it kicks in. Okay, so now we have a 2-dimensional creature, this triangle, and it has the property that there are only 2 degrees of freedom here. You can choose like 2 different ways of deciding them, but you can like choose this way and that way. 2 different choices between infinite number of values. And once you choose a point, you measure its dimension along P1, P2, and P3. Well, P3 is this way. I don't know how to draw it. But the coordinates, the projections and the coordinates, sum to 1. So this is the probability simplex for dimension 3. What does the probability simplex for dimension 4 look like? Anybody wants to guess the shape of the probability simplex? Triangular, what do we call a triangular thingy? Hint, Egypt. Thank you. It's a pyramid, it's a triangular pyramid. First of all, because it's k equal 4, we know that the probability simplex is of dimensionality k minus 1. That's 3. So we know it's a 3-dimensional object. And that object is a triangular pyramid. And it lives in a 4-dimensional space, which I don't know how to draw or to visualize. But I know that it lives in the corner of that space, or near the corner of that space. And I can actually, hold at least the manifold in my hand. I can hold the triangular pyramid in my hand and move around it and realize I have 3 degrees of freedom and that every point in that space corresponds to a 4-dimensional array of p's that sum to 1. Beyond that, I don't know how to go. Search on Wikipedia. Maybe somebody had some ingenious visualization tricks. So the reason we're talking about the probability simplex is because this is the world we will live in for a while. Now, imagine you're dealing with language and you're dealing just with words and you have a multinomial distribution over 100,000 words. So we're going to live in a 100,000 dimensional simplex, which is hard for us to think about geometrically, but we think about algebraically and logically. Oh, I need to let you go. Okay, so what we're going to talk about next time is different techniques for smoothing things to estimating multinomials and compare them. And we're going to take techniques that you're all familiar with, like adding 1 or putting a floor or putting a ceiling or interpolating different estimates. And we're going to try to put them on more solid theoretical foundation. Just like we did the maximum likelihood estimate. We all know what a relative frequency estimate is, but we didn't know that it was actually the maximum likelihood solution and why. So we're going to do something similar for other kinds of, types of smoothing. Okay, thank you. Yeah.